really have to show this out. I mean, you want to. But yeah, tell me at 3, actually at 4, we'll switch to the groundwater discussion. And you're going to read a nice paper like we did yesterday, okay? It's good? This is kind of a long day. Is this too much for one day, or we're feeling like we can learn something new? This is a lot, right? Can you maybe have a discussion while we get ready to ask, is there any capacity to learn? What I'm thinking about doing is this one, but what I'm thinking about something else. I want to see if people have Wow. Well, I mean, you must either, maybe you don't like to read, or maybe you like my stories. I don't know. Okay. Yeah, remote sensing. I made this picture. You guys all know what this is, right? This is your beautiful country, right? Myanmar. What do these colors represent? Do you guys know what this represents here?
Maybe the digital animation.
Yeah, maybe it's something about the elevation, right? So what does the greens represent? Low, right? We kind of have a convention within cartography. Cartography is like the study of making maps, right? We usually say, okay, green means kind of low, right? And then it's brown here. This is like the guide, yeah? Over here. This is the Shan Mountain. Shan Hills, yeah? And then what are these ones called over here? I don't know. Chin, yeah. I knew these were similar. I get that. This is Shan? Yeah. Shan. This is Shin. No, Chin. The same as Chin. Yeah. Okay. And then these ones up here are what? And you chin. Kachin. Yes. So chin, kachin. No, it's a kachin, chin, and then shan. Kachin, chin, shan. Yeah. Okay. So I'm really happy to know that now. And then there's some down here, right? Right. Small ones, maybe. Okay. How did I make this map? Where did I've never been to these places. I don't know how high they are, right? But what was this? When I used I used a DEM, right? The digital elevation model. And how did they make that? Did someone go out with the GPS every 90 meters? Yeah, it was acquired by satellites. Wow, this is like crazy. There's these things floating around in space that orbit the Earth that are taking images of the Earth all around. There's thousands of them now, and we can learn so much from them, right? So this is what this idea of remote sensing is about. I'm quite certain that there's a few gentlemen in the room that could probably teach this better than I will. So you help me if I miss something, okay? Help. I'm looking at the remote sensing. Goes back there. Okay. So just a little bit of a theory, introduce the concepts. What type of data are available, right? And then I think we'll probably not get to this, but if we don't get to it, this is the point I want to make. Remember those soda bottles we talked about in the last session, right? We call those are ground observations, right? Is that the soda bottle is kind of sitting on the ground. It's down here, you make a measurement, it's a ground observation, right? Now, there's also satellites measuring the same thing. These are remote sensed measurements. Are the two going to be the same? You know, measure rain from the satellite, measure rain from the ground. Are they the same? They're in the same spot, should they be the same?
ဘောတိုင်းနဲ့အောက်တိုင်းနဲ့ထပ်ပြီးကြပါ
They should be the same. Because the rain was the rain. I mean, the rain is the rain, right? But when we measure it, we get different numbers. Yeah. Which one do we believe? Do we believe the ground or the satellite? Usually we believe the ground, right? But see, the problem with the ground is maybe we have one here, we have one here, we have one here, right? We have these discrete points, right? But with the satellite, wow, we have it everywhere. It's continuous. You see the benefit? We have these ground points that we really believe. We have the satellite that gives us continuous data. We use the two, right, to correct, right, for each other. And then we get this beautiful picture that we hope is correct, right? We need both. We need both. That's the message. Okay. So, yeah, okay, hold on. Do you know that we are all doing remote sensing right now? Can you raise your hand? We are remote sensors. I am a remote sensor. You are a remote sensor. You know that? You know why we're remote sensors? I'm doing it with as many eyes as I can right now. Yeah?
အခုကျွန်တော်တို့ကိုယ်တိုင်တွေကဟိုလူအခုဦးကြီးကိုယ်တိုင်ဟောသဘုတ်ဆန်စာတွေဖြစ်တယ်ဆိုတာလက်ခံထားတယ်
No, I'm remote sensing, so are you. Yeah? Because guess what? I am not in contact with you. I'm not touching anybody, right? But I'm gathering information about you from a distance, right? So I'm gathering information from a distance. That's remote sensing. It's simple, it's easy, right? So it's doing something from a distance and learning something about the object. Remote sensing. We do it with our eyes. Now, what do our eyes do? How do they work? What's actually happening with our eyes? We see.
Yes.
Yes. What do we see? It's this thing what do we call these things? Light. We see light. What is light? Light is like this little sliver of this big thing we call what? The spectrum. The what type of spectrum? Someone's got to have this.
Yes.
The EMR?
No.
The electromagnetic spectrum, right? Okay? So, and we see this little range, right, of the electromagnetic spectrum, but it goes on both ways. There's all these things happening that we actually can't see. There's infrared, it's a little bit longer wavelength, that's about heat, right? Then there's ultraviolet, okay? And then there's cosmic rays, and there's radio waves, right? There's microwaves. There's all these different wavelengths. We're just sensing this tiny little sliver, but the satellites can see more. Have you ever seen those infrared cameras? They're pretty cool, like the night vision. Have you seen that in maybe a movie or something? If it's completely dark in this room, dark, completely dark, I cannot see you. But if I have a thermal infrared camera, I can see you. Perfectly dark, but I can see you. You know why? Because your body is emitting ultraviolet radiation. Infrared radiation. Infrared, yeah. And the hotter you are, the more infrared you're releasing. Okay? So that is remote sensing. It's the science of obtaining information about objects or areas from a distance. Okay, we do it with our eyes, but in terms of this application, it's usually from like satellites or planes or drones now. Okay? So, some things to think about is where are you observing the electromagnetic radiation from? Is it from the ground? Is it from the air, or is it from space? Okay. Now this is interesting here. This is important. When you do remote sensing, there's two kind of main ways of observing this radiation. One is called passive, one's called active. We make a quick little example of the difference, okay? So say I have a camera. Get my camera out. I have a camera. I have a smartphone, right? Okay. So I get my camera out and I take a picture of the wave. You guys, I'll take one over here. Okay. One. To be fair, two. Okay. What I just did, this is passive remote sensing. Yeah. Because guess what? The light that I captured by my phone is already being generated by these lights here, and it's being reflected off of your faces and the table, and it's coming to my camera. It's passive, right? Now, if I want to make this active, I put this thing on here called the flash. Okay, now the flash is on, okay? Now imagine it's dark, right? Now I take a picture. Did it flash? Yeah? Okay. I can't tell. It's not such a good example because it's so light already. But you know what just happened? That's an active observation. You know what? Because I created my own radiation that then bounced off and came back. And so I both emitted and received radiation. That's active. Okay? Passive is I'm just receiving. Okay? So this is, you never forget that. Active is like a flash. Passive is just like taking a picture. Okay? So those are two. Now I have 4 pictures of. Okay. So this is the electromagnetic spectrum, like you said. Yeah. And see this little window here? It's called the visible range. This is where we have the red, orange, yellow, green, blue, purple. Is there a song in Myanmar about the rainbow? Is there? Yeah, there? Yeah, like the colors of it's red, orange, yellow, green, blue, purple. In English, but I don't know. Can someone sing the rainbow song real quick?
See that?
I think I'm making you sing the rainbow song. You know it.
No, really. So we just learn in like scientific way.
Okay. Okay, so you have like an acronym or something?
Yeah.
Yeah.
No, only in English. That's the way I learn.
Oh, how?
Big jaw.
Okay.
Big jaw. Violet indigo.
Okay.
Green.
So you work this way?
Yeah.
Okay.
So we start with violet, indigo, blue,
Yeah.
green, orange. Yeah.
Okay.
Yeah.
Interesting. So we learned Roy G. Biv. So we do
Yeah.
it this way.
Okay.
Red, orange, yellow, green, blue, purple.
Yeah.
Roy G. Biv.
Yeah.
I like yours.
No, going from left to right.
It doesn't matter.
Yeah.
Yeah. Okay. So like I said, on either side of the visible range, there's other things happening, right? So these are longer wavelength phenomena. These are higher, shorter wavelength phenomena. Okay. And yeah, this one gets a little bit. I think I'll try to explain this. It gets a little bit tricky. Okay. You see this tan color here? This tan color here, if there's a lot of tan, what it means is our atmosphere around the Earth lets that wavelength go through. You know, our atmosphere is really important. It blocks these rays out here, gamma rays, cosmic rays. If our atmosphere let those go through, we would all die because we would have cancer. So our atmosphere protects us from these rays. You know how I know that? This atmospheric window, there's no ground here, which means that none of that radiation can come through the atmosphere. The atmosphere blocks it. It's like a shield, right? Okay? But then when I see a little bit of brown, this means like about 20% of ultraviolet is let through by the atmosphere. Okay? Which means, why am I talking about this? We have the Earth, right? Then we have the atmosphere, and then we have the satellite. If the satellite is trying to observe radiation on the Earth, but none of it can go through the atmosphere, we can't do that. We can't measure gamma or cosmic rays from the Earth, from space, because none of the rays would get through the atmosphere, right? Okay? But look here in visible. You see this? This is called an atmospheric window. This means that the atmosphere lets visible light through so that we can see the stars, right? We can see the moon. We can see the sun. This is really important. If we didn't have this, we would have no food. Because our plants wouldn't have the photosynthetically active radiation that they need to produce biomass, right? Matter. Okay, and then we have more atmospheric windows. Okay, infrared ones. And then we have some in microwave. Okay? So if we're going to design a satellite to observe the Earth, which wavelengths do we want to look at? Should we look at TV and radio? Should we look at X-ray, gamma, cosmic rays? Should we build satellites to measure gamma rays from space? Does it make sense? Should we do that? Yeah, I think some people do. Yeah, but
Yeah.
I don't know if it's important for everybody to really understand this, but you can try. Go on.
နှစ်ခုပါပဲအခုမျက်စိနဲ့မြင်နိုင်တဲ့ဟာပါလေခဏကဟိုနေရနေပြီးတော့ခဏအောင်ကြည့်တယ်လေအဲဒီဥစ္စာတော့ပြင်ပြီးသားအပေါ်ကနေဂျိုလူနဲ့ကြည့်ပေးမယ်ဆိုတဲ့အချိန်မှာလေဂျိုလူကကဘာဒီလိုရဲ့အချိန်မှာရှိနေပြီလေလူအတရားရှိနေပြီးသားဥစ္စာကြီးသူမြင်နိုင်တဲ့သူကနေတိုင်းနိုင်မဲ့အပိုင်းပေါ့လေဘလို့ဥစ္စာကိုတိုင်းရင်ကောင်းတယ်ဆိုစဉ်းစားအဲ့တော့ခဏကအာကာသတွေကနေရောက်လာပြီးတော့ဖြစ်တဲ့ဒီမှာ cosmic ray တော့ gamma ray beta ray အဲဒီဥစ္စာတွေကိုတိုင်းမလားဒါမှမဟုတ်လည်းပဲဒီအောက်ကရှိနေပြီးသားဖြစ်တဲ့ဟိုအယောင်ပြန်ပြီးတော့ reflection အနေနဲ့ပြန်ထွက်နေတဲ့ဥစ္စာကိုတိုင်းဖို့အတွက်ကြည့်ဖြစ်တာအဲ့ဒါကိုဂျိုလူကတိုင်းပြီးမယ်ဂျိုလူကဘာကိုတိုင်းပါဒီလိုမျိုးအဒီဘက်ကိုတိုင်းပါလားခရဘက်ကိုတိုင်းပါဒီလိုမျိုးဘယ်ဟာကိုတိုင်းရင်ကောင်းလဲဒုလဘယ်လိုတိုင်းပြီးကောင်းခရဘက်လားအဒီဘက်ဟုတ်လေဒီကပါကဲလေလေပဲဒါဘယ်တော့ကိုလောက်အောင်ဒီဘက်ကခရဘက်အဒီဘက်ဒီတော့ညာဘက်တော့အဒီဘက်တိုင်းပဲဆိုလို့လူပြညာဘက်လည်းထောင်လို့ညာဘက်လည်းအဒီတိုင်းပဲလူပြโอเคအဲ့ဒါခရတိုင်းပဲလူပြဘယ်ဘက်လည်းထောင်ရမှာဟုတ်လားဟာခဲလူများဘယ်တော့မတိုင်းဘူးပေါ့ဒီတဲခါလိုက်တော့ဘာတိုင်းရမှာမလို့ဘာပြရမှာမသိဘူး okay so we have like 5 from the on the red side and 5 on the violet side and the rest is we don't know yeah
So the moral of the story is that this is quite confusing.
Remember, they don't really know what to measure with the satellite.
Okay, yeah. And the main point here is all you have to really catch from this is that this brown here means that we can measure it from space. So like if there's brown in the wavelength, you see the wavelengths are changing here? If there's some brown, it means we can measure it from space. We can measure the Earth from space. And that's because the atmosphere lets that radiation go through in and out. Okay? It'd be like this, okay? Say I'm a satellite, Dr. Tim is the Earth. Yeah? Okay. If I'm looking at cosmic rays, I see nothing. The atmosphere that separates us, this is an atmosphere, it blocks everything. So I look, nothing. None of the cosmic rays go through the atmosphere. That's here. Yeah, but if I look for visible light, the atmosphere lets all of that go through. It's like it's transparent. I can see. Yeah? And then same for microwave. Look at this. Look at all this brown here. I can see microwaves from the Earth. But if I look for TV and radio waves, the atmosphere blocks it again, makes a shield. It's like this. It's like I'm looking from here. This is like radio waves. This is like microwaves. Okay? This is the atmosphere. So all you need to know is that if there's brown, you should make a sensor on a satellite to measure it. And if there's no brown, then don't make a satellite to measure it. And the thing is that we can learn really special things in these atmospheric windows. For instance, we can measure soil moisture with microwave radiation. Remember soil moisture, that's a change in storage. We can measure that we can't measure that with visible light. It doesn't work. But we can with microwave. We can measure the temperature of the Earth with infrared, but we can't do that with X-rays. And with infrared, we can measure the whole surface of the Earth, the temperature, okay? And then like visible, we can measure maybe what's water and what's not water. Or maybe we can measure what's vegetation and what's not vegetation. See NDVI, That's kind of the near infrared visible spectrums here. Okay, we kind of, this is pretty hard stuff, but I think we caught something. Okay, so here's a whole bunch of satellites. This is the picture again. They're moving around the Earth and they're taking pictures, just like me. It'd be like if I'm in space, I'm floating around and taking pictures of the Earth. Yeah, just like a satellite. That's all it's doing. Okay. Beautiful pictures that it takes. Okay, so that's kind of some theory. So just to review that, and I think I have a Kahoot, so maybe we just keep going. Okay. So what types of things can we observe about the Earth with this remote sensing, right? Because to connect it back here, right? These numbers here, yeah, why are we talking about this? You should be thinking, what is he talking about? Why are we talking about this? You know why? See these numbers here? These are hard to measure. We talked about that. They're hard to measure. We can use remote sensing to help us to get some of these numbers, okay? So that's what we'll talk about now. Okay. This is a quick summary of some of the things we can measure that have to do with water, okay? So this one here is land surface temperature. You can measure the temperature using infrared. Okay? We can measure snow cover. There's different indices we can use, different wavelengths to measure snow cover. That's important. Remember, change in storage, snow is important for that, right? We can measure rainfall. Remember, we have the trim, chirps. I have the chirps data I'll share with you for Myanmar. We have net primary production. You agricultural folks maybe know the net primary production. Net primary production is a measurement of all the green matter that was produced from photosynthesis. You can measure that with a satellite. We can measure radiation, and we can measure the greenness of the Earth. This is the normalized difference vegetation index, NDVI. Maybe you've heard of NDVI. Probably the most common remote sense product. Okay. So, do you guys use Google Earth? Do you guys use Google Earth? Yeah. You use Google Earth? It's such a cool tool. It's another free thing that I use this a lot to look at the Paleo Basin to try to get a feel for it, you know, in the fall. Anyways, use Google Earth, please. This is we get beautiful pictures from satellites. That's one thing. Okay. Digital elevation models. Remember, this is called the Shuttle Research Telemetry Mission, SRTM. That's where a lot of this digital elevation model comes from. You can read more about that on the website. Yeah, again, the temperature of the surface of the Earth. We can use that for all sorts of really interesting things. And I think, okay, we're doing okay. Okay.
I think there will be updates should I like just go to pick up on it?
Yeah. Let me just try to explain real quick, and then you do this first. Okay. This is really, really important. Of these fluxes over here, right? ET is really hard to measure. Really, really hard. We can't see ET, right? It's invisible. So how do we measure it? Okay. This is one way to measure it with satellites. It's called the surface energy balance. Okay? And there's 4 things we have to know to understand it. Okay? 4 things. Okay. This right here represents the amount of energy or radiation coming from the sun. Okay? So that's the input. This is just like the water balance. Remember the water balance? This is the energy balance. It's the same thing. In has to equal out plus the change in storage. It's the same thing now we're talking energy, right? So this is in, is radiation, right? That's all the energy comes from the sun. And that energy can do 3 things. 3 things, okay? It can either heat up the air, right? it can heat up the land, or it can change liquid water to water vapor. Those are the three places the energy goes. So radiation comes in, it can heat up the air, you feel it, oh, it's hot. Heating up the air. It can heat up the ground, oh, the ground is hot. Or it can change liquid water to water vapor.
အခုဒီထဲမှာဘယ်ခေတ်ရနဲ့ပဲပြောကြည့်လိုက်ကျွန်တော်တို့တိုင်းလို့ရန်တိုင်းတိုင်းလို့မရတာလားကြီးကြီးတိုင်းလို့မရဘူးဟုတ်ပြီနော်တိုင်းလို့မရတာပြီးတော့အမသားတွေကနေပြီးတော့ရောက်လာတယ်နေရတယ်ပေါ့လားဒီကပြောတော့ရောက်လာမယ်အားရမှာရှိတယ်အာဟုတ် variation အဲ့ variation ကအခုရထွက်လာတယ်အဲ့တော့ဘယ်လောက်ရှိတယ်ဆိုတာအားကဒါကိုကိစ္စကိုထားလို့ရတယ်ထားလိုက်ပြီးတော့လို့တော့တရားရလာတဲ့ဥစ္စာမှာဆိုင်အဲ့ energy ကိုသုံးတယ်အမင်းတပင်ရှိရင်အဲ့ energy ကိုသုံးတယ်ပြီးသုံးနည်းနဲ့သွားဒီကသုံးနည်းနဲ့ပဲဘာလို့လဲအခုထွက်လာပြီးတော့သူ့ပေါက်ဝန်းကျင်မှာရှိတဲ့လေသူ့ပေါက်ဝန်းကျင်မှာရှိတဲ့လေလေးပေါ့အဲ့ဒါလေးကပူမလာဘူးလားပူလာဒီချိန်ထဲမှာပဲလေမြေကြီးရလည်းပဲပူလာအဲ့ဒီချိန်ထဲမှာပဲအငွေ့ပြန်မှုအတွက်ကလည်းအငွေ့ရေငွေ့ပြန်ပါဖို့ရေကနေရေငွေ့ပြန်မှုဆိုရင်ဘာလို့ လဲ energy သုံးလိုက်ဒါဖြစ်ရင်ဒီ equation ထဲမှာကျန်တဲ့သုံးခုသိပြီးသွားပြီဆိုရင်ဟိုမှာလွယ်လွယ်နဲ့ပြန်နှုတ်လိုက်မရဘူးလား EG ကိုတွက်ချင်ဝင်လာမဲ့ energy ဘယ်လောက်ဆိုတာကျွန်တော်တို့သိတာပြီးသားရေကြီးရဲ့ temperature ဘယ်လောက်တက်လာမလဲလေရဲ့ temperature ဘယ်လောက်တက်လာမလဲဥစ္စာကိုပြန်နှုတ်ပေးလိုက် ET ရဲ့ပမာဏကိုတွက်လို့မရဘူးရပါပြီနော်ရပြီရှင်းလားအားလုံးရှင်းလား
Okay, good. Yeah. So if we can measure or estimate this we can measure with satellites, right? Well, before I go farther, how many equations are there? How many equations do we have? Remember before, how many equations? One equation, right? So how many unknowns can we have? One. Okay, so let's look through this and see, can we measure or estimate 3 of these 4, and then the 4th one we'll solve for. Okay? So let's think through it. Remember, this is the one that's like really hard. We're probably going to try to solve for that. Okay. So we can measure with satellites radiation. Okay? So check. Good. Okay. Now, this is called the sensible heat flux. It's like the amount of energy that goes to heating the air. Okay? And if we go outside right now, it's hot. You know why it's hot? Because the sun's energy, some of that is going to heating up the air. So hot. Sensible heat flux, right? Okay, we can actually measure that with either satellites, this is the difficult part, or it's better to have thermometers on the ground, measuring the air temperature, okay? Then this ground heat flux, we can also measure the land surface temperature, we talked about that. We can also make some assumptions or make some models for how to deal with that. Okay? But the point is that we can measure this, we can estimate these 3. And we can solve then for ET. You see? ET, well, first of all, in equals out, right? So in has to equal all 3 of those out. We just rearrange the equation here. So we move the G and the H to the other side. With what's in. Now we can solve this. So this is Wim. Remember the guy who I told you maybe the last training he's going to come. He's a really smart guy. He was like one of the first people to do this with satellites to measure ET. It's kind of like a real scientist, right? And he can tell us more about this. But yeah. Anyways, this is really cool stuff. Precipitation, yeah, we can get really nice data about precipitation. This is one example. It's called the Global Precipitation Measurement. It's a NASA and JAXA, so the Japanese Space Agency collaboration. We won't go into the details of how those work. It's fairly complex. Land use and land cover. This is important, isn't it? Now, is this a flux? Is land use and land cover, is it a flux? Do you see the land use, land cover here in this equation? It's not, right? Yeah, well, it's down here, but this is the equation. There's land use here, No. But it helps us split the fluxes into the water accounts, right? That's what's important with land use. Okay. So soil moisture, river flow, this is kind of a new one. It doesn't work super well. But you can get estimates of flow from rivers with satellites. If you are interested in this stuff, please read about GRACE. I'm not going to go into it. It's gravity recovery and climate experiment. It's really, really cool stuff. Measure the change in groundwater storage. But it's a really cool story. Not for now. This is what you get from GRACE. Looking at groundwater depletions in India, here in the north part of India. Okay, I think we stopped there. Yeah, actually, we have a couple minutes, so I'm going to do this one thing here. You remember this picture? This is the last picture we'll look at, or second to last. This is the Kathmandu Valley, right? And what we did is we took 6 different land use classifications, right? So this is like built. This is like low density, high density. So this means like it's almost all houses, right? This means it's kind of like half houses. Okay, then this one is like a forest, and this one is like shrub, and then this one is rice, and this one's non-rice. Both agriculture though. So 6 different land uses. Then we went out into the valley and we measured those 6 in different places in the valley, right? But we just have these dots now. But we want a continuous map, right? So then we can take satellite data every 30 meters and combine it with these ground observations of these different 6 land uses and transition from this picture to this picture. And isn't this cool? Because look, you can see the Kathmandu Valley. You can see Bhaktapur, you can see the Kathmandu, Alipur, you can see the highways, the roads here. So this is the Kathmandu Valley. You can see the forests on the outside, some of the agriculture here, some of the rice, right? And this is what we need for water accounts. Now we have a land use map, so we can do our water accounts, right? We need to do this for the Palais. Maybe we already have it from Emi River, but we need to maybe check. We do some ground truthing, right? Okay. There we've seen this picture. These are the different land uses. Okay. And it all comes from thanks to these guys. Okay. Yeah, we'll stop there. Are there any questions? I think we need to do some reading. I think, or maybe reading will be even worse. Maybe we'll fall asleep. Yeah, Kahoot. Should we Kahoot and finish? I think it's pretty low. It's just the first page. Yeah. Okay. So we stick this in. Well, the point is that you can't talk about water. Okay, so we make a compromise. This paper, if you're not like an engineer or a hydrogeologist, maybe it's a little technical, right? That's okay. What we want to do is we want to just read the first page, okay? So the first page, and also I'm going to add one thing to it. If you go to the last page, the back, right about here, it says, in summing up this technical discussion. You see that one right here? So from here, to read this part, and then read this part. Okay, so we just have 2 things we're going to read. We're going to read this one and this one. So these 2 columns. And then on the back, we read from right here and here. Maybe it takes, I don't know, what is it, 15, 20?
Yeah, sorry. 10.
Yeah, so maybe 20 minutes to, is that too long or too short? Because we're not going to read the whole thing, just the front page and then maybe half of the back page. Okay? Yeah, from something else. Exactly.
Actually, ဒီနေ့နာတော့အကောပေါ့နော်ဒီကအဓိကဒီပုံလေးကိုစာနဲ့တွဲမြင်နေတယ်လို့လေဒီပုံလေးနောက်အနောက်ဥစ္စာကြတော့လေဟိုရေးရတဲ့ဥစ္စာတွေပြန်ပြီးတော့နှိမ့်ချုပ်နေတယ်ကြီးချုပ်ပြီးရတယ်ဥစ္စာလေးနော်အဲ့ဆိုရင်ရှေ့ကတက်ကဟာလည်းကြက်ပါပါမယ်လေပါတယ်ပြီးတော့ဒီနေရာမဟုတ်တဲ့လူများနေကြတယ်နည်းနည်းလေးသူ့ဟာလည်းခက်ခဲရှိတယ်ဒါမှမဟုတ်အလဲကဒီဟိုဘရာဘူးဥစ္စာတွေနည်းနည်းလေးကြော်လာပါလေနော်အဓိကတော့ဒီရေကိုဘယ်လိုခွဲသလဲဆိုတဲ့ဥစ္စာကိုဘယ်လိုခွဲသုံးလို့ဆိုတာသိဖို့အတွက်ဥစ္စာဒါလေးကိုဖတ်မှရမယ်ရှင်းမျက်နှာ7မိနစ်နောက်မျက်နှာ7မိနစ်ဆိုရင်လောက်ပါပြီနော်
I think maybe we read for say 15 minutes and then maybe we discuss again like we did yesterday.
Okay. So for now, in a minutes, yes, so we get a 15 minutes or something. That is 4-5 now.
Okay.
So can that 15 minutes?
Yeah.
Okay. Also, later I say allow you and get a swing job. Okay? Now,
We'll have some people take some naps.
some people are already reading. They're so immersed in reading that they can't even say
Good.
On the second page, it's good to read this. Stop. First page.
Okay. Can we take the next 5 minutes to, this is a hard paper, it's old. Even for me, the English is kind of old, a little bit of a hard question, but can you talk about the notes, the questions, maybe the key things maybe you caught from this with your neighbors for 5 minutes? Okay, so just have a dialogue about your key questions. Now, if you're really catching this, there's this question I want you to try and answer. What are the 3 sources of water derived by wells? This is the main point of this paper. Okay? And then if you get this one, then I want you to try to answer this question. For sustainability in the long term, pumping must be matched by the sum of the water. These are 2 questions. These are tough questions. Try to have a discussion, see if you can figure out the answers to this. They're in this paper. More important to try to understand. Yeah, I'll give you a little hint now. I'm very focused. Okay, these questions here, this one, you know, on the last page, number 2, 3, and 4 answered the question. But start with number 1. Okay, so number 1 gives you the background, and then number 2, 3, 4 answer this question. It's kind of tough language though, but read the number 1, 2, 3, 4 on the last page now. Focus just on that. Okay, just 1, 2, 3, 4. Okay, just a couple more minutes, and we'll talk about this together. Okay, I hate to interrupt. You guys are very good students, very diligent, focused. But I think we're going to run out of time. So if this is interesting, you can keep reading all through the night, all night. There's so many papers on Google Drive, you can stay up all night with me. I'll be making the materials for tomorrow all night, so you can stay up with me. Okay? I'll be working you guys for it. Okay? So this question, this is our key question. What are the 3 sources of water derived from well? What that means is when you pump a well, you pull water out of a well. We've all done this. We have the hand dug well, right? Where we put the bucket down, get the water out. There's those wells. There's also the tube wells, right? We have a pipe, goes down, we put a motor maybe in there, pump the water. It's the same thing, it doesn't matter. when we pull the water out, where does it come from? I like to tell people, maybe there's these little creatures, little dwarves, down in the ground that make the water. When we pull it out, they just go like this. I don't think they get that far. Yeah, okay. The point is in the ground, the water is not being made in the ground. There's no new water coming from the ground, right? The water from the water cycle comes from precipitation, right? So when we pump a well, it's not like there's like somehow new water coming from the ground. The ground doesn't make water, right? We know that. So where does it come from then? So that's our question. So we have three places, three sources. So the first source is explained in number 2. Well, first of all, let's talk about number 1. What number 1 says, I'm on the last page, right? Last page of this paper. Okay, number 1. All water discharged. That just means pumped. Same thing. All water taken from a well is balanced by a loss of water somewhere else. What is that? Do we know what that's called? That's called the... Isn't that the conservation of mass? Isn't that what that is? Just kind of a complicated way of saying it, but, right? It just means water is not created, it's not destroyed. When we pump water, it has to come from somewhere. There's no, like, making of new water from the rocks or something, right? Okay. So number 1 is this, conservation of mass. When you pump the water, it comes from somewhere, okay? So number 2, so where is this somewhere? There's 3 somewheres, there's 3 places it comes from. Number 2, what does number 2 say? Okay, can we read the first sentence together? Just the first sentence. Can someone read it for me? Can we want to read it? Just the first sentence. Okay, sorry. Number 2 in the last page. Yeah. Maybe you were.
No,
I'm sorry. We are not on the same page. Okay, we are on the last page. I'm sorry for not making that clear. So last page, and then over here at the bottom left. So number 1, 2, 3, 4. Maybe that's why there was confusion.
Yes.
Yeah.
Number 2
Can someone read the first sentence of number 2? Can you read it? Yeah. Okay, listen.
And this lot is always to some extent, and in many cases, largely for storage in the aquifer.
Okay, so number 1 said that the water comes from somewhere. Conservation of mass. Number 2 says that it comes from, to a large extent, storage. Yeah. Okay? So that means like the water between the sand, between the gravel, between the soil, that water can be taken out by the well. And it can kind of dry that part of the aquifer out. That's called storage, right? That's the first place this water comes from. What do we call that? When the storage near a well gets taken away, it makes what we call a cone. Yeah, what do we call that cone? The cone of... Yeah, the cone of sadness.
Yeah, the cone of sadness.
No, this is the cone of depression. When we start pumping, there's no cone, right? You pump harder, it kind of starts to grow. Pump more, oh, it grows. Yeah? Keeps on going like this, okay? So that water, now this is air. There's no more water here, it's air now, okay? That water is going to our well. Okay? So that's number 1. So when we pump a well, primarily and especially early on, it comes from storage. It makes a cone of depression, right? Now, can we read number 3? Do you want me to read it or someone else to read it? This is maybe a long sentence. I will read it, okay? After a long time, I'm going to paraphrase. After a long time, this cone of depression will reach an area of recharge. Okay, and if you pump harder on the well, some of that water will come from the recharge. that would have otherwise been rejected. Okay? So I kind of paraphrased. So can we look at the example again here? So here I am. Can you pretend to be recharge?
Yes.
Okay, he is recharge. How do we explain this? Okay, I want you to imagine that Dr. Tin represents the aquifer, okay, and he is full of water all the way up to his head. Yeah, he's like full of water, right? So when it rains, can the water go in? Can it go in? No, because it's full. So where does it go? It flows off. Maybe it transpires or evaporates, right? It's full, okay? You be the full up.
Yes.
Now I'm the well. Okay. So I'm the well, so we start to pump. The water pumps. What happens? The cone, right? First thing, storage goes away. Storage. Okay? Oh, look, it's getting close to Dr. Thin. Ooh, I think maybe I'm going to get some recharge here, right? Keeps on growing, and then at a certain point, watch. See this water table? It pulls some water off of his head. So now when it rains, what can happen now? See, it can come in now, and it can flow to the well. You see, before the water was up here, it would rain, and it just runs off. Yeah, but now it's like, oh, look. Now it can come here, right? And as I pull it even farther down, look at this. Even more water can flow to the well. Okay? So what's the first thing? The first thing is storage. And the second thing is, if there's a really simple term, it's called induced recharge. Now, induced means like the well is causing it. So an induced recharge. The recharge otherwise would have been rejected. No recharge. That's before the well, it's rejected. After the well, it's induced. Okay? So that's number 2. So what's the first one? Storage. Okay? And we can say maybe change in storage. Right? Change in storage comes from change in storage. Number 2, induced recharge. It's because my cone has reached the recharge that used to be rejected. Now it's induced. Okay? Physically, that cone has to go all the way to the area of rejected recharge. Physically. This could take a long time, like thousands of years if it's a big aquifer. If it's a small aquifer, it happens maybe overnight. If it's an artesian aquifer, this could happen in days, weeks. Artesian aquifers behave very quickly because there's no storage you have to remove. It's just pressure. Yeah? It's very interesting. It's the piezometric change, not the storage change. Okay, so that's 2 things. So we have storage and we have induced recharge. Okay, now I need chalk. Sorry, I need you to be a river. Okay, so you come over here now. So we have our. Can you imagine that? I should have done this reverse because you're taller.
Yeah.
Can he be the recharge now? He be the because he's taller. You see? Okay. So see how the water over here is full? He's the recharge now. Yeah, and then he's the river. Okay? Yeah? So if the water is here on the river and the water is here on the mountains, the recharge, which way does the water flow? Remember, water flows downhill, right? So he's higher, he's lower. Which way does it go? This way, right? So it's flowing from the recharge area to the river. Okay? When it reaches the river, it comes. How do I explain this? Is it easier for water to flow through the soil or in an open channel above the ground? Which is easier? Open channel. Yeah, much less resistance, right? Right? We have this Manning's end for open channels, but Manning's end is very much lower compared to the hydraulic conductivity of soil, or rock. Okay? So when the water gets here, it goes, oh yay! I have the highway, right? This is like the slow walk through the jungle, right? But when I get to the river, it's like I get on the expressway, right? So I'm coming from the recharge slowly, and then all of a sudden, zoom, right? I hit the river and I go, okay? Okay, so that's the natural condition, okay? Now we put me in the middle. I'm a well again, right? Okay, so I start to pump. So what happens? First thing.
One is expanding.
Oh.
No.
Yeah, and what am I doing? I'm taking water from where? Where's it coming from?
First, recharge.
Storage. Because it's my cone, has it touched the recharge? Has it touched the discharge? It's not yet, no? Okay, so I keep going. Maybe you need to come closer for me. Okay, it's good. My hands aren't wide enough. Okay, so I'm growing, right? Now I start to get kind of happy. I hit the recharge, right? So what happens? I start to take water from here, right? Now, guess what? The water that used to go to discharge to the river, I start to take that too. So now I'm taking new recharge, so that's induced recharge, and I'm taking what would have gone to discharge, right? So induced recharge, reduced discharge. You see? There used to be maybe, think of it like this, there used to be 10 units of water coming in as recharge, flowing through the aquifer and going to the river. 10 in, 10 out. Mass balance, right? The aquifer was full. Okay? Then I come in and I take 5. Okay? I pump, and all 5 comes from storage. Storage. And then I go, ooh, okay, I'm going to take 3 from over here and 2 from over here. Okay? So now what's happening? There's still 10 recharge, right? The 10 comes into recharge, but 5 of it is going to me. How much ends up going to the river now? Only 5. Because I took 3 from here and 2 from here, so he's only getting 5 now. I get 5, 10 coming in, he gets 5. You see? So that water is coming from induced recharge and reduced discharge. Okay, so what are the 3 things? Number 1, storage. Number 2, induced recharge. Number 3, reduced discharge. Okay, let's go one more time. So storage, induced recharge, and reduced discharge. You see? Okay. Now, what I want you to imagine now is that you guys, can you go all the way to the pole over there? You go all the way over to you're very far away now, yeah? Yeah? If they're this far away and I start to pump, it could take a long time before I can get there, right? And in the process of pumping, where is all the water coming from while I'm going out? Where is it coming from? It's coming from storage, right? And so the water levels here are going down. Maybe there's a city here, and maybe the water levels keep dropping because it can't reach the discharge. It can't reach the recharge. It just takes storage. And imagine this. Maybe there's 10 recharge, 10 discharge. That's natural, right? Say I start pumping 20. This is what happens in California, by the way. So 10 in, 10 out. That's the natural. I say I want to grow lots of food. I'm going to pump 20. Okay? So I start to pump 20, and where does it come from? Storage. Yeah. 20, 20, 20. Okay? Now I start to hit recharge. Maybe I take 5 from recharge. I hit discharge. Maybe I take 5. Is that enough? I have 5 and 5, but I'm pumping 20. So what happens still? Storage. Wow, now I can pump and I will never get enough recharge or discharge. There's not enough water. So what happens? It continues to go down and down and down and down until what? It's gone. The reservoir is dry. We do this in the US. It's crazy, right? We do this in Pakistan, India, right? Now, you guys are blessed with lots of water. I don't think this is happening anywhere anymore. Because you have lots of rain. Maybe it doesn't come at the right time, but please don't do this. This is a mistake. We need to know what's sustainable. Is it sustainable for me to pump more than the recharge and the discharge that I can take? Is that sustainable? No. And by the way, what happened to this river over here? Remember there was 10 coming in and then 10 going out. So my river had 10 in it, right? My river had 10, okay? The fish had 10, the 10,
All the people.
yeah, for the people, right? Navigation, yeah. When I pump 20, what happens to the river? Well, is it less water or is it no water?
That's one.
Yeah. If I pump 20 and there was only 10 to start with, if I take 5 from him, how much does he get now? No. He doesn't get anything. You know why? Because there used to be 10, right? Coming? Yeah, but I'm taking 5 from him and 5 from him. There's nothing left for the river. You see? So what is the stream? What happens to the stream? It goes dry. This happens in California. Our streams go dry because we pump too much. And don't do that. It's not good. Now the Yama River goes dry because of the geology and the hydrology. It's okay. But don't make streams go dry that aren't dry. That's not good. Right? So does this make sense? Yeah? Okay. I like the thank you. You were wonderful. Yeah. Thank you. Okay. Okay. I think can I show you some pictures of this and then we'll finish? I'll show you a picture of what we just talked about. I think we get it. Okay. I skipped this. Okay. You see this? Water comes from a combination of change in storage, induced recharge, reduced discharge. You know this now. Yeah? Okay. Now, here's the thing. If you pump more than the induced recharge and the reduced discharge, if you pump more than that, remember the example of 20, what happens to change in storage? It always goes down. Always. And that is the definition of unsustainability, right? Because this is using a resource unsustainably. At some point, it will be gone. Okay? And Tice came up with this idea of capture. So he said, okay, the sum of these two is what the well can capture. And if you're pumping more than what you can capture, you will always remove water from storage. And that's not good, okay? So we make a picture of this. This can take thousands of years, 10, 100,000 years to come into some sort of new equilibrium, new balance. And this is the thing, unless pumping is balanced by capture, changes in storage will continue forever, perpetually. Pumping is unsustainable. That's what we just talked about, okay? So we make a picture of this now. Okay. So here is a river in California. It's called the Cosumnes River. Okay, this is the natural state. We have lots of rain. We have this beautiful river. It's down in the valley. The rain causes recharge, and that recharge flows to the river as discharge into the river, and then it flows. Okay, beautiful. Okay, we put in a well. Let's say we put in a well here. We put in a well here. We start pumping water. What is this called here? This is the cone of depression, right? Okay. And the water that used to be here, remember the water here? Now the water's here. What is this? We took water from storage. Yeah? Okay. Okay, now wait a second. Can I go back? The water used to be going like this. Right? So this was what's called a gaining stream. The water was coming to the stream. When we look at this picture now, what is the water doing now? It's going from the stream to the aquifer. This is a losing stream. Yeah? Remember, I dried him up. I dried Dr. Tin up like this, right? And you know what? Even worse? You can actually disconnect the stream. This happens too. Where the water table actually drops, so there's an unsaturated zone. And if you continue to pump, guess what? The stream can go dry, right? Now this is in Nepal. I think it's the same idea. I'm gonna just kind of stick to this paper here. Yeah. So again, water table in the stream. You pump through this well. You can then reverse it so that water's coming from the stream to the aquifer. And then you can disconnect and make it so it's losing. And what that ends up with is like this. This is a dry stream. Okay? Okay. This was hydrogeology introduction. Because I think your IWUMD, when they asked for this training, they asked for training on sustainable, yeah, it doesn't say that here, but in the original paper it was sustainable groundwater management. There was something specific about groundwater. That's why we talk about this. We can't do water counting and think about sustainable groundwater until we know where water comes from when we pump a well. Right now we know. We know where it comes from. Where does it come from? Three things. Storage. Now, induced recharge doesn't happen very much. It's kind of smaller. The big ones are storage and reduced discharge. Okay, those are the two big ones. Okay, so you guys are experts now. Hydrogeologists. Now we have new hydrogeologists. Okay. Yeah, so I think we have to stop. It's 5. We skipped the Kahoot, unless you guys want to stay here and do it, but I don't think we go, right? And we start again at 9 tomorrow. Does that sound good? Okay. What's that? What did you say?
I think she wanted to stay involved.
If you want to stay and do a Kahoot, I mean, yeah. The brave at heart. Okay, thank you for your attention and participation. Tomorrow we're going to do some real pencil paper calculations about precip and stream flow. Okay.